A review of the tutorial for how to calculate precision, recall, F1 score, and more for deep learning models with a minor adjustment to work on current Keras version, Keras 2.1.2.0. Let's see the next section, which is tutorial overview. This tutorial is divided into 3 parts. They are: binary classification problem, multilayer perceptron model, how to calculate model metrics. Here is the next section, binary classification problem. It is called the two circles problem because the problem is comprised of points that, when plotted, show two concentric circles, one for each class. As such, this is an example of a binary classification problem. The problem has two inputs that can be interpreted as x and y coordinates on a graph. Each point belongs to either the inner or outer circle. The example below generates 1000 samples, with 0.1 statistical noise and a seed of 1. Once generated, we can create a plot of the dataset to get an idea of how challenging the classification task is. The example below generates samples and plots them, coloring each point according to the class, where points belonging to class 0, outer circle, are colored blue and points that belong to class 1, inner circle, are colored orange. Okay, now, we will run the code. Running the example generates the dataset and plots the points on a graph, clearly showing two concentric circles for points belonging to class 0 and class 1. Scatter plot of samples from the two circles problem. Here is the next section, multilayer perceptron model. We will develop a multilayer perceptron, or MLP, model to address the binary classification problem. This model is not optimized for the problem, but it is skillful, better than random. After the samples for the dataset are generated, we will split them into two equal parts, one for training the model and one for evaluating the trained model. Next, we can define our MLP model. The model is simple, expecting two input variables from the dataset, a single hidden layer with 100 nodes, and a ReLU activation function, then an output layer with a single node and a sigmoid activation function. The model will predict a value between 0 and 1 that will be interpreted as to whether the input example belongs to class 0 or class 1. We will fit the model for 300 training epochs with the default batch size of 32 samples and evaluate the performance of the model at the end of each training epoch on the test dataset. At the end of training, we will evaluate the final model once more on the train and test datasets and report the classification accuracy. Finally, the performance of the model on the train and test sets recorded during training will be graphed using a line plot, one for each of the loss and the classification accuracy. Tying all of these elements together, the complete code listing of training and evaluating an MLP on the two circles problem is listed below. Let's run the code. It might take a bit time to be completed. Running the example fits the model very quickly on the CPU, no GPU is required. The model is evaluated, reporting the classification accuracy on the train and test sets of about 83% and 85% respectively. The plot suggests that the model has a good fit on the problem. Line plot showing learning curves of loss and accuracy of the MLP on the two circles problem during training. Let's see the next section, which is how to calculate model metrics. The Keras metrics API is limited and you may want to calculate metrics such as precision, recall, F1, and more. One approach to calculating new metrics is to implement them yourself in the Keras API and have Keras calculate them for you during model training and during model evaluation. For help with this approach, see the tutorial. How to use metrics for deep learning with Keras in Python. This can be technically challenging. 3 metrics, in addition to classification accuracy, that are commonly required for a neural network model on a binary classification problem are: precision, recall, F1 score. In this section, we will calculate these 3 metrics, as well as classification accuracy using the scikit-learn metrics API, and we will also calculate 3 additional metrics that are less common but may be useful. They are Cohen's kappa, ROC-AUC. This is not a complete list of metrics for classification models supported by scikit-learn. Nevertheless, calculating these metrics will show you how to calculate any metrics you may require using the scikit-learn API. For a full list of supported metrics, see scikit-learn.metrics, Metrics API. Classification Metrics Guide. The example in this section will calculate metrics for an MLP model, but the same code for calculating metrics can be used for other models, such as RNNs and CNNs. We can use the same code from the previous sections for preparing the dataset, as well as defining and fitting the model. To make the example simpler, we will put the code for these steps into simple function. Now that we have a model fit on the training dataset, we can evaluate it using metrics from the scikit-learn metrics API. For more help with making predictions using a Keras model, see the post. How to make predictions with Keras. We can make the class and probability predictions with the model. The predictions are returned in a two-dimensional array, with one row for each example in the test dataset and one column for the prediction. The scikit-learn metrics API expects a 1D array of actual and predicted values for comparison, therefore, we must reduce the 2D prediction arrays to 1D arrays. We are now ready to calculate metrics for our deep learning neural network model. We can start by calculating the classification accuracy, precision, recall, and F1 scores. We can also calculate some additional metrics, such as the Cohen's kappa, ROC-AUC, and confusion matrix. Now that we know how to calculate metrics for a deep learning neural network using the scikit-learn API, we can tie all of these elements together into a complete example, listed below. Okay, now, we will run the code. The code gets error because the function, predict_classes is deprecated in current version of Keras, which is Keras 2.12.0. Actually, for binary classes we do not need to use predict_classes, and using a threshold of 0.5 on the logits returns the predicted class for us. Okay, now, we will run the code. In this example we have binary classes. If there were more than 2 classes we could get the predicted class by finding the argument or column index for the maximum predicted value for each observation.